Good afternoon. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka. Well, we are having a lecture series on A-level chemistry. This is my 27th lecture, and it will be on organic chemistry. I named this 27th lecture as Organic Chemistry 2. Well, in the organic chemistry lecture, 26th lecture was on organic chemistry 1, and it was introductory organic chemistry, and we started with the alkane and naming of alkane according to IUPAC, and then we stopped there, and now we start a little bit of that one again, the how rules and regulations applied of IUPAC to name the aliphatic or organic compounds, I would say. So we have been talking about alkanes. Now I go for the next slides where we will be naming alkenes, another homologous series of hydrocarbon. So the rules applies for alkanes, and alkanes are same according to IUPAC. Only thing that the branching, etc., will be a little bit different. Here, for example, the alkanes, the first two members of alkanes are ethene and propane. These two members we can name it ethene and propane. But when it is more than 4 carbon atoms, I would say, then we name it a little bit differently, depending on where the double bond of alkenes are, in which one. For example, we take I said 4 or more carbon atoms. If we have 4 or more carbon atoms and to name the alkenes, then we look for the double bond first, and then we name it. If it is, for example, it was butene, we said but1ene. It is, this double bond is carbon 1, therefore we said but1ene. And similarly, here you say if it is in 1 or 2, we take the lower number. If it's double bond between 1 and 2, we take the lower number and name it as but1ene. But if we come to and used to indicate at the start of the bond, using the same rule, if we take this one, then it is, you see, it is bonded with 1, 2, 3, and therefore we call it is bonded, the double bond is between 2 and 3 carbon atoms, and therefore we name it but2ene. Okay, so there we start naming like this, and that will be discussed when different functional groups will come, and we name it according to IUPAC system. Here we see ethene and but1ene, propene and but2ene. You see numbering, we're taking the numbering and then naming the alkene compounds. Well, we talk about a little bit of physical properties of alkanes and alkenes. And see, the bonding in alkanes or alkenes we discussed while we were discussing in the lecture of chemical bonding. Very well, we talked about weak intermolecular forces and the intermolecular forces increase. How does it? So here we will see that the simple molecules these are bonded together by weak intermolecular forces, and as the carbon atoms gets higher, the intermolecular forces increases, and once the intermolecular forces increase, the bonding is a little bit strong, and therefore higher the carbon atoms, the melting point and boiling point temperature also rises. Well, at room temperature and pressure, what happens? C1 to C4 of alkane, I can say alkane, are gases, and those of C5 to C17, it is liquid, and C18 and upwards are solids. Like the alkanes, melting and boiling temperature of alkenes also increases, the carbon atoms increase in the molecule. Ethene, propene, and butane are gases at room temperature. Alkene, like other hydrocarbons, do not mix with or dissolve with water. We have to remember the bonding we discussed, the sigma bond and pi bond. You will see we said hybridization of bonding, that means atomic orbital and then molecular orbital, we said. And then we said if atomic orbital overlap head-on, and that becomes sigma bond. And in alkanes, it's a saturated hydrocarbon, carbon and hydrogen bonds are always sigma bond. And alkenes, you see that we do not have, we do have a double bond, and here we also get a pi bond here. Pi bond is not in saturated hydrocarbon, but pi bond is we do get in unsaturated hydrocarbon. So pi bond is it's sidewise overlapping of atomic orbital, and that's what we see here in this alkene, that this one of this carbon-carbon bond is sigma bond and another is pi bond. So bonding, we have to remember that hydrocarbon, if it is saturated hydrocarbon, we get always sigma bonds between carbon and hydrogen, or between carbon and other functional group. But if it is unsaturated hydrocarbons, then we get sigma bonds and pi bonds between carbon and carbon. And we also get, if we take acetylene, then we will have carbon-carbon triple bond, in that case 1 sigma bond and 2 pi bonds. We have discussed it while we were talking bonding. Then comes isomerism in organic chemistry. Why carbon atoms so many compounds? That's the first question I raised. Why carbon atoms have so many compounds? One of the reasons is that it is sometimes possible to join same atoms together in different ways. Same atoms together in different ways. An example, this is a butane, is it not? But there is another molecule, 2-methylpropane, which has molecular formula, same molecular formula. Here it is. It is butane, and here it is 2-methylpropane. What we have, that it's all carbon-carbon single bond, and then we have hydrogen here. You see that the carbon atom here is attached with another methyl group, and that molecular formula is same, but we call this 2-methylpropane. 1, 2, 3 propane, 2-methylpropane. So compounds like butane and 2-methylpropane, they have same molecular formula but different structured formula. And because of this same molecular formula and different structured formula, we call the structural isomers. There are 2 structural isomers in butane, but 3 structural isomers in carbon when it is C5. And if we go for C6, we get 5 structural isomers. You see here, number of carbon atoms increases and number of isomers increases rapidly. For 1 carbon atom, it's 1 isomer, 2 carbon atoms, 1 isomer, 3 carbon atoms, we have 1 isomer. When it is 4 carbon atom, we have 2 isomers. When it's 5 carbon atoms, it's 3 isomers, and so forth. We can have, you see, with 30 carbon atoms, how many isomers? millions of isomers we can have. Okay, then we are talking about structural isomers and divided into 3 different types of structural isomers. One is chain structural isomers. What is chain structural isomers? It have different chain of carbon atoms. This is butane, and you see 2-methyl propane. It is different chain of carbon atoms, and that's what we call structural isomers. Chain structural isomers. Positional structural isomers have different positions of the functional group. Here it's a propan 1 ol, propanol. Here propan 2 ol. You see the functional group are in different positions, but we have the same molecular formula. Similarly, functional group positional structural isomers, different positions of the functional group. And here third one is functional group structural isomer have different functional group in it. Here it's this is what is it? Propane 1 ol, an alcohol, and that here it is the different functional group. There is methyloxyethane and in ether. So there are 3 structural isomers, 3 different structural isomers. One is chain structural isomers, another is positional structural isomers, another functional group structural isomers. We take stereoisomerism then. Here, if we define stereoisomerism, what we see that stereoisomerism are compounds whose molecules have the same atoms bonded to each other, but with different arrangement of the atom in space. Same atoms bonded to each other, but their arrangement is different in space. And that is what is stereoisomerism. And we have 2 types of stereoisomerism. One we call geometrical stereoisomerism, another we call optical isomerism. Geometrical one, either cis or trans isomerism, like carbon-carbon single bond. There is no free rotation about a free rotation. There is free rotation, but unlike carbon-carbon single bond, I said unlike carbon-carbon single bond, in alkene, it's a double bond, and therefore it has got no free rotation about the double bond. This type of isomerism is unsaturated organic compounds. We get in unsaturated organic compounds, and we call it geometrical isomerism. And what happens? We see what are the groups attached in it. So there is 1,2-dibromoethane. It is called cis because the bromine atoms are attached in same side of the double bond carbon atoms, and similarly here hydrogen atoms are in the same side. Here it is not in the same size and the same side, and therefore we call it trans 1,2-dibromoethane, cis 1,2-dibromoethane, and trans 1,2-dibromoethane. These are geometrical isomers. We said that the same atoms bonded to each other, but the arrangement, spatial arrangement, are different. Whenever we have unsaturated compounds with structure, we can have the geometrical isomer. These 2 isomers have different arrangement, as you said already, and they have different physical and chemical properties too. Okay, and go for that. The optical isomerism. Here, if a molecule contains a carbon atoms that is bonded to 4 different groups of atoms, 4 atoms or different groups of atoms, 4 different atoms or 4 different groups of atoms, it can form the optical isomers. Example, here you see this is one group of atom, this is another, this is another, this is another atom. or group of atom. It's not same, or any of the two or any of the three could not be same atom. So 4 different atoms grouped in carbon atom, and there we can have optical isomer. We can describe this carbon atom as asymmetric carbon atom. It is asymmetric carbon atom because it is not grouped with any symmetrical atom. So, and this carbon atom, because there are no plane of symmetry in its molecule, that these 2 different optical isomers called enantiomers are mirror image of each other, but they are not superimposed. Mirror image of each other, and this one is the chiral center of this optical isomers. Chiral center. This carbon atom is chiral center. Okay, we go for here now. If we talk about organic compounds, we know that thousands and millions of compounds we can have in organic compounds, and then we have to read types of organic reaction and reaction mechanism. We have to understand it properly, know what it is, how it is happening, these sort of things. So it is useful to explain organic reactions by summarizing the overall reaction in a series of steps. It's useful, you see, explain organic reactions by summarizing the overall reaction in a series of steps, and that series of steps together we call it reaction mechanism. All chemical reactions, whatever it's maybe organic or inorganic, it's involved breaking and forming of chemical bonds. Breaking and making of chemical bonds. First, bonds are breaking and again forming also. There are 2 ways in which covalent bonds can break. Why you are talking about covalent bonds here? Because in hydrocarbon we do have all covalent bonds. So there are 2 different ways of breaking covalent bond. One is homolytic fission, another is heterolytic fission. We now talk about little bit of homolytic fission and heterolytic fission. Homolytic fission, type of covalent bond breaking bonding electron pair. We have, this is a covalent bond. We have a bonding electron pair. If we break this one and take away we know that we have shared 1 electron of hydrogen here and 1 electron of chlorine here, and then share this pair of electron and forming covalent bond between this, example hydrochloric acid. So if we break this bond and each atom takes its electron with it, then what we do get, we get, you see, this is what we get. We get an electron with hydrogen and an electron with an unpaired electron with chlorine. And this is how it happens, and there is an electron with hydrogen and another unpaired electron with chlorine. And we call this free radical. So when we have this sort of fission, we call it homolytic fission. That means we form free radicals by breaking the bond, which is called homolytic fission. We take the heterolytic fission. Well, it is a covalent bond, and you know that we have electronegativity difference in covalent bonding, so which makes it polar covalent bond. So the heterolytic fission is this type of covalent bond breaking, bonding electron pair, lip electron to each from forming free radicals. That was homolytic fission. And heterolytic fission, what happens? Uneven breaking of covalent bond. What is uneven breaking of covalent bond? That is, we have atoms bonded together covalently, there are electronegative atoms and electropositive atoms sharing a bond pair of electrons forming bond, but then the electronegative one nuclei will pull this bond more to itself. If we break this bond, let's say if we break this bond, what happens then? This electron pair pull it in way and then break it, and we get this sort of cation and anion. This sort of cation and anion bracket. Here it is. This electron pair, it goes to more electronegative atoms and forming a negative ion, and also as well as a positive ion. So that's what happens for heterolytic fission. Heterolytic fission can also form it XCX bond. X is a more electronegative than carbon, CX bond, X. And here you take an example of this, that methyl bromide. Here is methyl bromide. So its bonding pair electron here is moved more towards bromine and forming bromide ion, and this methyl cation, which you call it carbocation. The positively charged carbocations often appear in organic reaction mechanism. So in the next slide, we will talk a bit of three types of carbocations, specifically primary, secondary, and tertiary carbocations, their stability and how they form, these sort of things we will take in the next lecture. And thank you very much for your attention of this Organic Chemistry 27th lecture. Hope we will have another session, another lecture in 28th lecture, where we will discuss more about organic reactions and reaction mechanism. Thank you again.